The journey of atomic power has left many a disaster by the roadside, as different designs and working principles were tried out, as well as the odd human error. The subject of this video is an incident that would push forward reactor operation experience, albeit at the expense of a partial meltdown. It seems that a certain place keeps on popping up in the comments sections of my videos. And after reading the title, then you atomic aficionados will have a pretty good idea of where I mean. Today we are looking at the sodium reactor experiment at the infamous Santa Susana Field Laboratory. Trust me, we'll be looking at this place as a whole in another video, as there's too much to talk about in this one video about the SRE. The sodium reactor experiment was a proof of concept for a type of reactor that made use of liquid sodium as a coolant, instead of the more common water. The experiment sought to be able to provide enough heat for use in commercial electricity generating applications. The benefits of this type of reactor is that the coolant does not act as a moderator, as well as not needing the coolant to be held under pressure, as liquid sodium has a wider total temperature range to water, 785K compared to 100K. In a water-cooled reactor, the water has to be held under pressure to avoid the coolant boiling off. But before we get into the technicals, let's have a brief history of the Santa Susana Field Laboratory, which is where the SRE was located. The SSFL, which is around here on a map, was a government testing facility between 1949 and 2006. The site was used for testing of rockets, space program equipment, most notably for the Apollo missions, and what you are all here for, nuclear reactors. The site was divided into areas called 1 to 4 and also had 2 buffer zones. The site was selected due to its remoteness, somewhere away from the prying eyes of civilians, and to reduce the risk of contaminating any populated areas due to the risk of explosions and the like. In total, 10 reactors were opened at Santa Susana over the years, and along with them came various atomic related endeavours. For example, a fuel fabrication facility, a hot lab used for cutting up irradiated fuel, and possibly one of the worst ideas ever, an open sodium burn pit, where radiated and chemically contaminated items were just burnt in a massive open fire pit. Oh, and the hot lab also caught fire at one point as well. Pretty much a massive radioactive dumpster fire. The site's reactors, which were considered experimental, didn't have any type of containment in their buildings. So, you know, the big thick concrete walls and domes that most modern reactors have. So that was also a great idea. The site, when it was wound down in 2006, created a horrendous headache that still continues today in terms of the cleanup efforts. And as always with the internet, the place has some pretty hilarious Google reviews. Now that we've addressed the wider area that the SRE was placed in, let's finally get on to the subject of this video. Now, plans to test liquid sodium cooled graphite moderated reactors were announced in 1954 by the Atomic Energy Agency, and construction began on an Atomics International designed facility. The reactor was designed to be a flexible testbed for various different types of fuel materials and different levels of enrichment, as well as experimental types of cell cladding. Construction began in 1955, and local energy company Southern California Edison installed a 6.5 megawatt steam electric power generating plant to make use of the heat created by the experiment. The reactor building of the SRE consisted of a high bay area, a side bay area, and a hot cell facility. The side bay contained the control room, administrative offices, electrical shop, and air conditioning equipment. The high bay area, known because of its high roof, housed the reactor and its primary and auxiliary cooling systems, a new fuel storage, irradiated fuel storage, a fuel handling machine, and a moderator handling machine, which handled the graphite moderator cans. The reactor undertook controlled fission for the first time in April 1957, and in November a small town called Moore Park became fully powered from the reactor, albeit for just an hour. The design was different to most modern reactors, as the whole unit was built in place instead of being prefabricated. The reactor containment structure consisted of 3 main parts and was below ground level, the first of which was the cavity container. The container was the outmost containment vessel for the reactor and was 23 feet high and 14 feet 8 inches in diameter, and was constructed of 1/4 inch carbon steel. The cavity liner was bolted to a wall surrounded by 4 feet concrete, forming the biological shield and the support for the whole reactor. Next came the outer tank, made of 1/4 inch thick alloy steel. This vessel was 18 feet 11 inches high with a diameter of 12 feet 6 inches. It was sealed to the cavity liner and underneath sat on insulated blocks. The space created by the insulated blocks is called the insulation cavity, and was filled with nitrogen gas to prevent the coolant from coming into contact with the outside air in the event of a coolant leak. The outer tank's main job was to act as a secondary containment of the sodium coolant, and finally is the core tank. This was where the reactor core was situated and was sealed to the outer tank. At the top of the tank, helium was held under a pressure of 3 psi. This was known as the cover gas. Excess gas was sent to a waste gas decay tank. This is to stop contaminated gases leaking to atmosphere. The core tank was made of 1.5 inch thick stainless steel and had a diameter of 11 feet 3 inches. On top of this was the top shield plug, which sat inside a ring shield. This was rotatable and weighed 75 tons. The top plug had 81 small plugged holes and 2 40-inch and 1 20-inch larger holes. The SRE used graphite as its moderator. This was used to slow down the neutrons to get more use out of the fuel elements. The graphite moderator elements consisted of hexagonal blocks just under 11 inches wide and around 10 feet high. These were known as cans. Each can was placed 11 inches centre to centre from one another, allowing a small gap between each can for coolant to flow. The gap was approximately 0.013 of an inch. The moderator cans were wrapped in zirconium alloy sheets to help enforce spacing as well as protect the graphite from the sodium penetrating it. Inside the reactor core there was space for 119 cans, however not every one was for a moderator. Around the outside of the core were reflector cans. These were used to reflect stray neutrons back towards the centre of the core. Through the reactor core ran 81 vertical tubes. These were used for fuel, safety and control rods and were accessible via the small plugs on top of the rotating shield plug. Right, whilst we're on the subject, let's talk about the fuel assemblies and how they were made up. Each fuel assembly is made up of 7 fuel rods. Each rod was 6 feet long and had 12 fuel slugs inside. Each fuel assembly was lowered through one of the 81 openings in the reactor's top shield and inserted into the core region of the reactor. Each assembly had a hanger rod connector on top of it. There were in total 43 fuel rods used during operation. The reactor had 8 control rods. 4 of these were safety rods which formed the automatic shutdown facility known as SCRAM. These rods contained a boron on nickel alloy. The SCRAM facility was controlled automatically but also had the ability to be activated by operators from the control room. To enable quick activation of the SCRAM facility, the safety rods are held out of the reactor by magnets. If disengaged, the rods would enter the core by the power of gravity. And during normal operation, the safety rods were not inserted into the core region. Next, we have 4 more control rods. These were split into 2 groups of 2, but they did very similar actions and were limited in their total movement whilst the reactor was in operation. The first of these were called the shim rods. These were used for fine regulating adjustment of the power of the reactor. The next 2 were regulating rods, and these were used unsurprisingly to regulate the power of the reactor. These were limited in their movement to only 7 inches by the reactor control system. The 4 rods are used to manage the neutron population of the reactor core during operation. They didn't have a SCRAM facility, but they did help keeping the reactor under control and were the main mechanism for safely bringing the reactor to initial criticality during startup. Like the safety control rods, the regulating rods contained a boron nickel alloy. Right, the final bit of the reactor I'm going to cover is the cooling system. Using liquid sodium had its benefits, for instance not being a moderator. However, it had one big drawback. The liquid sodium becomes extremely dangerous when exposed to water or air by either exploding or catching fire. The liquid sodium coolant was split into 2 parts, a primary and secondary loop. The reason for the 2 cooling loops is to prevent contamination, due to the primary loop being in contact with the reactive materials inside the reactor. The primary loop circulated around the reactor vessel, taking with it heat from fission and passed through a heat exchanger. Inside the heat exchanger, the primary loop coolant passed through metal tubes. This in turn warmed up the liquid sodium inside the non-reactive secondary loop. After this, the secondary loop coolant made its way through a steam generator, which in turn powered a turbine connected to a generator. If a leak in the secondary loop became apparent, the use of 2 loops reduced the risk of radioactive sodium being released. The reactor didn't operate continuously due to the experimental nature of the project. Instead, it was operated in runs. In between each run, data was reviewed and the reactor components were examined for potential improvements. The operation of such a reactor as the SRE meant that the operators were working to what could be done in theory. However, theoretical and operational realities were not the same thing, and this would be found out over each subsequent run. The first 7 power runs between the 7th of July 1957 and the 25th of September 1958 saw the successful generation of electrical power, as well as a number of tests involving checking out the effectiveness of the Scram facility. Before run 8, the primary sodium was pumped back and forth several times between the primary loop and its primary fill tank. This introduced sodium oxide to the primary loop and ran the risk of causing blockages in the system. During run 8, operators noticed worrying inconsistencies in inlet and outlet coolant temperatures. This was put down to the oxide buildup in the coolant channels and on temperature sensors. The reactor was shut down and the coolant was filtered, and fuel rods 9 and 10 were removed for inspection as they had been running too hot. Upon removal, the rods were contaminated with a black residue. They were promptly cleaned and reinserted into the reactor core. For the remainder of Power Run 8, things didn't go to plan. Erratic temperatures, sodium oxide in the core, and the eventual confirmation of tetrilene in the primary loop showed that disaster was just down the road. Runs 9 to 12 continued to be plagued with erratic inlet and outlet temperatures, and more black residue was found on fuel elements. This leads us on to Power Run 13, the penultimate before disaster. The run took place between the 27th of May and 3rd of June 1959. On the 29th of May, a scram was triggered due to poor sodium flow rate. The next day the reactor was restarted, but things would go dramatically downhill from there. After run 13, again a number of fuel cells were examined and deemed to be contaminated enough to warrant cleaning. The tetrilene on the cells had blocked drain holes, allowing some sodium to become trapped. This would not have a great outcome. Whilst in the wash cell, which was an area near the reactor, around 18 US gallons of water came in contact with the trapped liquid sodium, and the inevitable happened. The explosion lifted the wash cell sealing plug 18 feet into the air. It was later found that no one had actually installed the hold down clips properly. Due to the explosion, no more fuel cells were washed. Leading up to run 14, the confirmed tetrilene contamination had to be addressed. This would be quite a large undertaking, as nitrogen gas had to be bubbled through the primary sodium loop. In preparation for the nitrogen gas purge, all helium inside the reactor had to be removed and replaced after completion. At 6:50 AM on the 12th of July, the reactor was brought into criticality for run 14. The operators were cautious during startup, reaching only 500 kilowatts at 8:55. Small but out-of-spec temperature fluctuations began within the moderator. This was expected due to the tetrilene contamination, and operators saw similarities from runs 8 to 12. Fuel channel exit temperatures, which normally should be similar, began to diverge, meaning that there were coolant blockages. The power level of the reactor was kept below 1 megawatt. However, at 11:42, the primary system automatically initiated a scram. This was due to a loss of auxiliary primary sodium flow. Just over half an hour later, the reactor was restarted at 12:15. And for the next few hours, the power was increased to 2.7 megawatts. At around 3 PM, something worrying was discovered: an increased radiation level in the high bay area of the reactor building. The pressure on the cover gas was reduced to try and slow down any leak. A member of staff in protective clothing entered the high bay area to take readings to try and locate the source of the radiation. A measurement of 500 millirems an hour was discovered over the shield plug near channel 7. By 5 PM, 25 rems an hour was recorded over channel 7 after the replacement of its shield plug, and at 5:30 PM the reactor was shut down. The next day, on the 13th, the reactor started to act even more erratically by experiencing a number of excursions, and rose in power without any operator action. At 5:28 PM the reactor was set at 1.2 megawatts, and as the operators gradually tried to increase power, the levels went higher than expected. The controllers were inserted to try and get back control. Over the next hour, operators struggled to keep control over the fluctuating power. At 6:24 PM, SRE's power level began doubling every 8 seconds. The operators manually scrammed the reactor at 6:25 PM. For the next few days, the reactor was started up and shut down several times as power excursions and erratic temperatures were recorded. On the 23rd, at 9:50 PM, the reactor shut down automatically due to an indication that the power was increasing too sharply. It was restarted again at 10:15 PM. The 24th saw some rather dangerous behaviour as operators attempted to try and free up blockages in some of the fuel channels by jiggling the fuel elements up and down. However, 4 elements seemed to be stuck in place. Again, the SRE was shut down automatically at 12:50 due to an uncontrolled increase in power. However, the indication of fuel cell damage was ignored by the operators, who had been convinced it was a faulty signal. The reactor continued to act erratically, and on the 26th it was shut down for inspection of the fuel elements that had shown the highest temperature increases. A camera was inserted into the troubled fuel channels and the results were worrying. In total, 13 fuel elements had been damaged, and whilst removal for inspection took place, channel 69's rod broke off, leaving over half of it stuck inside the reactor core. The damage had been done over the course of Run 14, and numerous chances to prevent disaster were either ignored or avoided. Multiple missed opportunities meant that the experimental reactor released radioactive elements into the building housing the unit. It would be later thought that the main fuel cell damage took place after the 22nd of July, but signs were clear to see in the power runs leading up to the event. However, it's easy to say this after finishing reading a report into the whole event, 60 years after the fact. It's important to note that clearly unsafe practices by today's standards, such as wiggling fuel rods, were not really thought of like that in the late 1950s and whilst operating an experimental reactor. Radioactive materials were released from the damaged fuel cells to the sodium coolant, and in turn to the helium cover gas. The cover gas was run through a filter and was stored into decay tanks before being vented to atmosphere. An internal document produced after the event stated that over a 2-month period, around 28 curies of fission gases were released into the atmosphere, which was within federal government limits. However, conflicting reports claim that up to 6,500 curies of iodine-131 and 1,300 curies of cesium-137 were released. But the poor data collection and recording at the time means it's very hard to know for certain. However, Rocketdyne at the time claimed nothing was released, which does seem a bit hard to believe due to the lack of proper confinement that the SRE building had. Now, you think this might have spelled the end for the SRE, but if you did, you'd be wrong, as the whole reactor building was cleaned up and pressed back into work in 1960, albeit with a new and improved reactor core. The event damaged around a quarter of the reactor core, and many lessons would be learnt from this, including improvements to the sodium circulation system, wash cells used steam instead of water, improved cladding alloys, and better fuel geometry was utilised. The SRE was shut down and decommissioned finally in February 1964. The clean-up of the experiment was rolled into the wider clean-up efforts at Santa Susana Field over the coming decades. Due to the nature of the field laboratory, so much contamination, both chemical and radioactive, has been reported over the last 60 years. I mean, it's pretty much expected when open sodium burn pits were used at the site. This makes it very difficult to pinpoint the damage to the environment caused by just one of the reactor incidents on the site over the years. In 2006, a board made up of independent doctors and scientists ruled that over the years, around 260 cancer-related deaths are linked to the test laboratory as a whole. The same panel also concluded that the SRE meltdown released 458 times the amount of radioactivity released into the atmosphere by the 3 Mile Island accident, even though the event actually created 10 times less contamination. This was due to a lack of confinement buildings at the site and other experimental reactors, bearing in mind that the TMI accident was fairly well contained within its confinement building. However, this is widely disputed in several conflicting reports, so you may have to believe what you want on this one. The cleanup efforts at Santa Susana as a whole still continue to this day, as all sorts of nasty materials have to be safely removed and disposed of. But this will most likely be a subject of a future video, as the SRE incident is only scratching the surface. Thank you for watching, I hope you enjoyed the video. I wasn't expecting this one to be this long, but there was just too much to cover. Would you like to see my videos before they are up on this channel? Then you're in luck. As for $1 per creation on Patreon, you can. Do you have any future video suggestions? Let me know in the comments. I've got a Twitter, so check me out on there. And all that's left to say is thank you for watching.